Greetings and welcome, friends. Mr. Waddy and his geometry class here today, talking about circles. We're starting a new chapter. It's a big deal. It's a big deal. Circles are not polygons. They're not made up of sides, but there's all sorts of interesting things that apply. Technically, nothing in the universe is perfectly circular, but we can all imagine the ideal of what a circle is. All right. So today we're talking about lines and segments that intersect circles. 10.01. A circle, in case you didn't know, is the set of all points in a plane that are equidistant from a given point called the center. Now, if I changed this word plane to being in a space, like 3 dimensions, then it would no longer be a circle, but it would be which figure? Solid. A blank is the set of all points in 3-dimensional space that are equidistant from a point called the center. What would that figure be? A sphere. Yeah, they actually have very similar definitions. So yeah, the center, like so. Look at that. You could talk about circle. You could even like draw a picture of a circle. There you go. And a circle is named by its center point, is what we end up labeling it as. And here's a whole bunch of vocabulary. We were just talking about this, my friends in real life and me, about special segments and lines in circles. So a segment whose endpoints are the center and any point on a circle is called a radius, right? There's a radius. A chord is a segment whose endpoints are on a circle. So there's a chord, right? Lots of possibilities there. A chord that contains the center of the circle is referred to as the diameter. Diameter. A secant is a line that intersects a circle in 2 points. All right, so here's a secant line. It's like a chord that was just like, what if I don't need to limit myself by the boundaries of this circle? What if I can do anything I want, and if I go forever in both directions? And then like it dreamed and it did it. It happened. Let's see. A tangent line is a line in the plane of a circle that intersects the circle in exactly 1 point. And this is perhaps like a weird idea, but even if we were to zoom in to the infinitesimal dimensions, right, just zoomed in on B there, it would still only touch at 1 point. And that point is called the point of tangency. Like so, you could have a tangent ray as well, a tangent segment. What was I going to ask? So a tangent touches a circle at 1 point, a secant at 2. Is it possible to have a line that touches a circle at more than 2 points? No, it would cease to be a line or a circle. Like one of those things would have failed to continue to exist as they have been defined. So, identifying special segments. All right, AC. What type of segment is that? Let's see. Oh, where's my cards at? Here we go. All right, we had a random volunteer radius. Let's see. Evan, AB would be what? The diameter, a diameter, because there are infinitely many of them, right? Jack, Isaiah, you guys with us? Anthony, here we go. DE is it's a ray here, and it's a tangent ray. All right, and it appears to touch the circle at exactly 1 point. And let's see, bonus question, Ty. Point B would be referred to as what point? Ty. The point of tangency. Yes. And let's see, AE, let's have Aiden M. A to E is what type of line? What are our thoughts? A secant line. A secant line. Which I'm sure there's some sort of joke there about what do you call a line that is blind? Maybe? I don't know. We'll workshop that one. We'll workshop that one. It's in there somewhere. So, how about this? Core concept. It's also possible to have tangent lines to multiple circles. That's interesting. All right, here, I'll fit that all on one page here. So, coplanar circles and common tangents. In a plane, two circles can intersect in 2 points, 1 point, or no points. So there we go. 2-point intersection, 1-point intersection. Look at this one's like on the interior of that circle versus the exterior. And it's possible to have like no point intersection there. Coplanar circles that have a common center are called concentric. Concentric circles, you might use those in describing, I don't know, like earthquakes or something. Which, by the way, your mobile you had of the planets going around the sun is probably false, because they did not travel circular paths around the sun. They travel elliptical paths, which are close to circles, and the sun will be at one of the focal points. Question, comment? Arguably, yeah. Yeah. Which actually, this idea of we all can imagine these perfect right triangle, a perfect circle. We can imagine these concepts, but they don't actually exist perfectly within our universe. But we all, like, in defining it, we're like, yeah, the set of infinitely many points that are equidistant from the center, we all have the same image roughly in our heads, right? And so it's something that we can imagine as to what the ideal is, even though it doesn't exist in our universe. So let's see. A line segment that is tangent to two coplanar circles is called a, come on, tangent. A common internal tangent intersects the segment, here, key word right here, the segment that joins the centers of the two circles. Okay, that's going to be interesting. So if I imagined the two circles having a segment that connected their centers, a common internal tangent would intersect that segment. A common external tangent would, however, not. All right, so let's keep going, friends, because these are going to get interesting. Ooh, example 2. Ooh, lovely. Here we go. Drawing and identifying common tangents. Tell how many common tangents the circles have and draw them. Use blue to indicate common external tangents. So let me draw some external tangents. So you could imagine, right, something like that and like that. If I could draw, you could use a straight edge if you wanted. This one, something like that and that. And this one would have 2 external tangents, something like that and that. You get the idea. It's all about the ideal, friend. And how about, let's see, red to indicate internal. You guys might not have those same 2 colors, but it's possible to have that and something like that. And the reason those are internal was if I drew the segment that connects the 2 centers, those internal ones would, in fact, hit them. It is possible to have these 2 circles to have one internal tangent that is kind of where you would attack a snowman with a sword if you ever were to have to fight a snowman. Yeah, like, yeah, if the snowmen came alive and for some reason were not peaceful like Frosty was. So there you go. Oh, right, yeah, Calvin and Hobbes. Ooh, wow. Someone should link out to some Calvin and Hobbes in the comments of this video. That would be pretty good. Also, I didn't tell you how many tangents there were for those, but you guys will count them. That's fine. All right, now, big idea here. The tangent line to a circle theorem. Wow, in a plane, a line, yeah, go to the long cabinet, tall cabinet, you can find some writing utensils there. In a plane, a line is tangent to a circle if and only if, so this is biconditional, the line is perpendicular to a radius of the circle at its endpoint on the circle. Always. That's what this is saying. It's perpendicular to the radius. So it's not perpendicular to this radius or this radius. Okay? It's perpendicular to a radius that happens to have its endpoint at the point of tangency. Okay? So that's kind of a cool idea. And tangent segments from a common external point are congruent to each other. And I think I end up having you guys do a proof of this one. Maybe I'm wrong. This one is definitely not drawn to scale. But these would be two right triangles. I don't want to spoil the proof. I'm not going to spoil it. What? I'm not going to spoil it. You guys? You almost had me spoil it. Not me. No, sir. So let's apply these. And I actually don't even know those ones by name. I just use them because they're great. All right, here's example 3. Is ST tangent to circle P? Is ST tangent to circle P? How could I do this? Yeah, what are our thoughts? Well, what about, now, it would be tangent if I could prove this is a right angle, correct? And I could prove that is a right angle by using the converse of the Pythagorean theorem, perhaps? So the question is 12 squared plus 35 squared equal to 37 squared? That's the question. And if that is true, then this is a right angle, and then ST is tangent. And this is true. Let's see. I guess I have a calculator here. I guess I'll do some numbers for you. I wonder if there's like YouTube channels of people that just like type in numbers in a calculator and you could just like watch it if that was like a thing that calmed you down. It is a YouTube trend. I didn't. Okay. All right. And 1225 plus 144. What? That's true. And therefore, ST is tangent. And that means that 12, 35, 37 is what special set of numbers? What type? A Pythagorean triple. Let's see. All right, finding the radius of a circle. Ah, ha, ha. I love these. I love it. All right. Haley, you're going to help us out with this one because I drew your card. It says, in the diagram, point B is a point of tangency. So, Haley, what do I know about AB and BC with respect to each other? The right angle. Okay. Find the radius R of circle C. Let's see. Let's have Isaiah help us out. So Haley and Isaiah together. Let's set up Pythagorean theorem. I'll get us started. R squared plus, Isaiah, what else could I do here for R squared plus what squared? 80 squared is equal to, and Haley and Isaiah, what do you guys think the hypotenuse is here? Yeah, or I'm going to write it as R plus 50 because I like putting my variables first, but you are 100% correct. All right. And in order to expand that, you might have to recall the square of a binomial pattern, which is a plus or minus b all squared is equal to a squared plus or minus 2ab plus b squared. Yes, Isaiah? We know it's a right triangle. Oh. So alternative. Well, but I don't know this angle yet. How do I find it, though? So tan of A would equal R over 80, but I've got two unknowns here. So that is a true statement, but I've got two unknowns. So I would need one other fact. But I like your thinking. All right, so let's see. R squared plus, what's that, 6,400 is equal to, now guys, I've got to use this pattern up here. R squared plus 100, R plus 2,500. So guys, let's solve this for R. Now it's a quadratic, but notice what happens conveniently. If I subtract R squared from both sides, they actually eliminate each other. So you guys are so lucky. You almost had to solve a quadratic equation, which I conveniently just posted a video on how to do this morning. Wow. For my Algebra 1 buddies. Okay, so let's see. Let's have oh, that person is not here. Jack, here we go. Jack, how do I solve this for R now? All right. I like it. I like your thinking. Now, what I don't like is trying to subtract this in my head for some reason. All right. 3,900. Okay, and then divide. So, guys, so far, like, the last part of this problem has all just been algebra. So my R, which sometimes looks like a square root symbol, is 39. And I like that. I like that. Let's see. Let's do example 5 here. Question, yes. I used this pattern up here. A was equal to R, and B was equal to 50, and I plugged it in this pattern up here. Great question, by the way. So R squared became R squared, and then plus 2AB. This is the square of a binomial pattern, and it's the way that you appropriately expand a two-termed expression that is being squared. The other way you could get that is if you do R plus 50 times R plus 50 in parentheses and FOIL it out, or double distribute it. But if you remember this pattern from Algebra 1, you'll be able to expand it as such. So I did 2 times 50 times R, and I got 100R just like that. All right. Which also, I believe I've got in my multiplying polynomials video from Algebra 1, posted probably a week or two ago. You could also check that video out if you'd like some help. Maybe someone could tag it in the comments or something. Here, let's take a look at example 5. Which, one of my math department compatriots referred to this as the Dunce Cap Theorem. The idea of you've got like a sideways dunce cap sort of thing. But no one knows what that is anymore. RS is tangent to circle C at S. So that's a 90-degree angle. Let's see, who's going to help me out with this one? We're going to have Lauren help us out here. Okay. So CT is also perpendicular because RT is tangent at T. Lauren, what do I know about these two tangent lines here? They are congruent to one another. And then, by def of Kong, what's an equation I could write that might help me find the value of x? If those two segments are congruent, then their lengths are, yeah, and mathematically we call that equal, right? So 3x plus 4 equals 28. And let's see, someone here, Malik, how do I solve this equation? I like it. 3x equals 4, and then divide both sides by 3. Good old Algebra 1 days. And I get x is equal to 8. So, let's see. There's some other interesting problems. I think we're good for this video. So thanks for watching, internet friends. Special shout out to, what's Robert's last name? Robert Paterno. Special shout out. Thanks. Bye-bye.